heparin has been changed. They've modified it, made these much smaller versions. These are administered subcutaneously, so they're given as an injection into the subcutaneous fat, usually once a day, and they again work in a mechanism that I can't recall the exact details of, but again, they don't directly bind to the clotting factors and inhibit them, but they activate something else. I think they activate something called antithrombin 3, but don't quote me on this. This is just sort of like old knowledge that I haven't had to use for a very long time. But I think they work by activating an endogenous protein called antithrombin 3 that then inhibits the clotting factors. So they activate something else that inhibits the clotting factors. But again, they don't work in the way that warfarin works by stopping the clotting factors from being produced at all. So those are major examples then of anticoagulants: warfarin, the DOACs, and the heparins. So, back to warfarin then, talking about warfarin. So we said that warfarin works in the liver to stop the clotting factors being produced. You can reverse warfarin with vitamin K. And the reason that you can reverse warfarin with vitamin K is that the way in which warfarin works to stop the clotting factors being produced is by inhibiting vitamin K. So, warfarin is what we call a vitamin K antagonist, or a VKA for short. It inhibits vitamin K, and vitamin K is extremely important in the enzymatic reactions within the hepatocytes that produce the clotting factors. And I'm not going to go into detail of this synthesis pathway because I no longer know it. It's not something that I need to know clinically, but the basic understanding that I do still retain from preclinical science is that if we have a hepatocyte here, the hepatocyte produces the clotting factors. So here a red arrow, and here's a clotting factor that's being put into the blood. And the way in which it produces these clotting factors involves enzymes, and these enzymes need vitamin K in order to function. So they are using this vitamin called vitamin K. Warfarin then inhibits the vitamin K. Again, I can't give you more details than that. This is the sum of my knowledge. But remember that famous interview with Feynman, who was the great physicist, where he's asked, I think, some question by some interviewer about why is ice slippery. And I think the interviewer wanted him to explain it using quantum electrodynamics or something along those lines. You know, one of the pieces of science that Feynman worked heavily on. And I think Feynman gave what seemed to the interviewer like a really obtuse answer. He said something along the lines of, because ice is just slippery. And the interviewer was then pressing him, the interview becomes more and more sort of like tense, with the interviewer saying, I don't think that's an unreasonable question. Please, can you explain why ice is slippery to me? And then Feynman just sort of refuses to go beyond saying that ice is just slippery. And then he tries to explain to the interviewer how actually when you're asking why questions, you can always go deeper. You can when you're asking why, never does it get to the point where you can't ask why again. You can ask why continuously. No matter how deep an explanation you go, there's always deeper. You can always ask why again. And at some point, you have to eventually get to the point where the answer is just, you have to accept that is the way, that is a law of nature, or that is an accepted point at which we don't ask why anymore. That is an accepted fact. And Feynman was basically arguing, what's the point? Why are you actually asking me to go deeper? Why don't you just accept that it's an accepted fact that ice is slippery? Because even if I give you deeper and deeper explanations, does it improve your understanding? Well, I suppose it does, but eventually you will get to a point where you just have to accept something. So why don't you just accept it at the stage where ice is slippery? Anyway, that's what I'm kind of saying here. This may seem very obtusely simple, but actually I don't need a deeper explanation. I don't have any utility for a deeper explanation in clinical practice, therefore I don't need a deeper explanation. this suffices, this model suffices, and I'm happy to accept this model as the foundation of my understanding. So, warfarin inhibits the vitamin K. Vitamin K is needed for the enzymes which produce the clotting factors. So, if you give someone warfarin, it goes into the hepatocytes, inhibits the vitamin K, and therefore inhibits the synthesis of the clotting factors. You can then reverse it by giving huge amounts of vitamin K. If you give someone an enormous amount of vitamin K, then it doesn't matter that the warfarin's there. It's not going to be able to inhibit all of that vitamin K, and therefore the enzymes inside the liver will start to produce the clotting factors again, and clotting factors will be put into the blood, and the anticoagulant effect of warfarin will be diminished. And this is how we reverse warfarin. And we have to do this quite regularly. So if someone is on warfarin, and let's just discuss reasons that people can be on warfarin. So one of the major reasons is that they have a condition called atrial fibrillation, which I realise I've just gone down a rabbit hole with. Now I'm going to have to explain atrial fibrillation. So AF, full name atrial fibrillation, is a condition of the heart that generally happens as people get older. It's a condition that I don't really know a good way of telling you how to avoid getting it. Certainly, if you have other diseases of the heart, you're more likely to get it. So if you have coronary artery disease, i.e. ischemic heart disease, you're more likely to get atrial fibrillation. If you have high blood pressure, which can lead to then remodeling of the cardiac muscle, that makes you more likely to get atrial fibrillation. If you have valvular disease, again, that can lead to remodeling of the chambers of the heart because of the strain that they're under trying to pump against the valvular problem, and that makes you more likely to get atrial fibrillation. But then some people will get atrial fibrillation just as they get older, even without all the other heart problems, just because the conduction system within the heart has degenerated somewhat and is no longer functioning properly. So what is this condition? So if we just draw a tiny simple picture of the heart here. So here are the four chambers of the heart, the two atria up here and the two ventricles here. So remember, this is right and this is left here. So remember, the atria contract together, push blood into the ventricles contract together and push blood out into, well, the pulmonary circulation in the case of the right ventricle, and then the systemic circulation in the case of the left ventricle. Now, normally, the heart beats nice and regularly. The initiation of the electrical activity that makes the heart beat starts somewhere called the sinoatrial node, which is a little area of tissue up in the right atrial area, SAN for short. So the electrical activity starts here, it spreads across the atria, they contract, it then spreads through remember there's a blockage between the atria and the ventricles, so the electrical activity cannot spread from the atria to the ventricles except through a tiny little gateway, a tiny little door, which is called the atrioventricular node, the AVN here. The electrical activity then comes down into the ventricles and makes the ventricles contract. That's normally how the electrical conduction of the heart works. Now, in the condition called atrial fibrillation, something goes wrong with the atria, and usually this happens when the atria are actually deformed. So usually the atria become much bigger than they should be. So in the elderly person's heart, the atrial chambers can become hugely expanded. Particularly, the right atrium isn't the big culprit, it's usually the left atrium. It becomes hugely deformed, and usually the reason for this is that the pressure inside the left atrium is too high, and reasons for this can be, for instance, if you've got hypertension, so far too high blood pressure in the systemic circulation, then the left ventricle is going to struggle to pump blood up into that really high pressure aorta, and then so the pressure in the left ventricle is going to be much higher, and that's going to go back into the left atrium and cause left atrial pressure to be much higher, because the left atrium's got to push blood into the left ventricle. So if the pressure in the left ventricle is much higher, then the pressure in the left atrium is also going to have to become higher, and that pressure then pushes out on the muscle, and gradually over years and years the chamber can expand and expand, so you get left atrial dilatation. Other things that can cause this by the same mechanism is if you've got aortic stenosis, again, that's the left ventricle is going to have to push blood against that stenotic aortic valve, and that's going to mean that the pressure inside the left ventricle and then the left atrium is going to be higher. Another example would be mitral regurgitation. So if the mitral valve is dodgy